Hello, welcome to everyone in this video. This is our lecture number 3 on statistical mechanics. In first two part, we actually discuss introduction and the micro canonical ensemble. Today, we want to discuss canonical ensemble on the part of the partition function, thermodynamic function of an ideal gas. So look at the syllabus of the Calcutta University 5th semester statistical physics. We actually cover up in the lecture 1, that is first one, that is microstate, elementary concept of ensemble, geodetic hypothesis and phase space we discuss in lecture number 1. In lecture number 2, we discuss the microcanonical ensemble, postulate of probabilities, Boltzmann hypothesis, entropy and the thermodynamic probability. Okay, in this video I want to discuss this portion, that is canonical ensemble, partition function and thermodynamic function of ideal gas. In the upcoming session we will be continue the rest of the part, that is the system of identical particles, Bose-Einstein statistic, radiation and Fermi-Dirac statistic will be discussed in the upcoming lectures. So let's start. What do you mean by canonical ensemble? In the last lecture, we discussed that the microcanonical ensemble, that is actually isolated system. That means no particle are transported, no energy are transported between the system and surroundings. But canonical ensemble is a closed system. That means no particle are interchange or the transfer between system or surroundings, but the energy transferred such that the system is in an isothermal process. That means the temperature will be constant of this system. So here the number of particle, volume and temperature, these are the macro state which are conserved in this system. So you can conclude the wall type, that is n is constant, that means the particle are not transferred through the system, that is wall is impermeable or impenetrable. Volume constant mean residual and temperature constant mean diathermic wall, that means heat is transferred such that the temperature of the system will be conserved. Okay, and you can compare with this closed system. Here the leading thermodynamic variable is Helmholtz free energy. You know, in the micro-canonical ensemble, the leading thermodynamic variable was entropy. From entropy, you will be obtain the others variable, or entropy can be changed into the internal energy. Internal energy can also find out the other thermodynamic variable. Here the main key thermodynamic variable is Helmholtz free energy. From the equation of Helmholtz free energy, you can obtain the others variables. Okay, so look at that. Now comes into the point, that is the partition function. Partition function actually, when you wants to find out the RS system of the energy ER, okay, the probability to finding the that RS system in the probability in the energy ER, that will be the energy variation, that is gi is the degeneration. This is the energy expression, that is Boltzmann's distribution law. So using this law, you just write down this summation is total and this one in the state of the ER energy state. Okay, so this will gives you like that, AR cancel out. This is actually taken as Z, which is known as the partition function. So partition function is the total arrangement like that. So partition function is actually the total arrangement which can be possible in this system. Okay, so this is the partition function, summation gr exponential e to the power er. Okay, now from the partition function you can find out the internal energy and then the Helmholtz free energy, and after that you will be obtain the others variables like that. So internal energy, that is the actually expectation value of ER, that is the average value of ER. So summation, this will becomes like that, summation ER probability of this R. So put this value of P of ER, which is just write down, this is P of ER probability. So you will be obtain this relation, and this is the Z. So if you taking the derivative with beta, you will be get this one. So this is minus z, del Z del beta, and this is Z. So in combination you can write that is the minus del beta of ln Z. So U is nothing but minus del beta of ln Z. Okay, you can change this into the expression of the temperature. So you know the beta equals to 1 by kt, so del beta del t is minus 1 by kt square. So you can change this derivative with respect to beta to from with respect to temperature. So you just change this chain rule, del beta ln z, that multiplied into the del beta del t by del beta. You can put this del t by del beta is minus kt square. So finally you can get the another expression of the entropy in terms of temperature. In terms of beta, that is minus del beta ln z. This is commonly used, and if you wants to find out the expression of the internal energy with respect to temperature, you can got this type of relation. From this internal energy you can find out the Helmholtz free energy. Okay, Helmholtz free energy F is nothing but U minus Ts. U is the internal energy, T is the temperature, S is the entropy. So if you take dF, you will be get du minus Tds minus sdt. And Tds, from the thermodynamics law, you know Tds equals to du plus Pdv minus mu dn. Mu is the chemical potential. Mu is the chemical potential. Okay. So I want to just write down the chemical potential here because is need to note it. That is chemical potential. Okay, chemical potential. Okay, so this is the chemical potential mu. So you just put this value of TDS into this expression, and here you can see that is du and du are cancel out. So finally you will be get this df equals to like that. So del f del t, that is the partial derivative with respect to temperature, you will be get this one, this at volume and number of particle are constant, so dv equals to 0 and dn also 0, so this will be minus s only. So the entropy S equals to minus del f del t at constant v and n. So you will be obtain the expression of entropy from this Helmholtz free energy. Okay, so you can see that is the Helmholtz free energy gives you the entropy expression. This actually helps you to find out the expression of the Helmholtz free energy. How? You will be get this F equals to U minus Ts. U minus Ts. This is replaced by del F del T at this one. Okay. So U equals to F minus T into this one. So these two can be combined as minus T square del T of E by T. You can see that is del T of F by T. F by T equal to derivative of t 1 by t is minus 1 by t square, and derivative of f is del f del t. Okay, so u equals to like that. So this minus t square into this can be written as del f of this, and minus t square, that is del t of 1 by t, integration derivative will be minus 1 by t square there. So this can be written as this one. I think you understand this one. Just calculate this, you will be got this portion. Okay, so del t can be cancelled out like that. If you take this kb in both side, both up and down, and 1 by kbt or 1 by kt is beta, so del del beta of this one. So u is like that, but you already obtained this u equals to minus del del beta of ln z. So if you compare these two things, you can easily find out the expression of f. F is the Helmholtz free energy. Finally you got f equals to minus kt ln z, where z is the partition function. This is the most important formula for canonical ensemble. This Helmholtz free energy is the key element in the canonical ensemble to obtain the other thermodynamic variable. How? See, we already find out S, but we can again repeat other thermodynamic variable. This F equals to U minus TS, dF equal to du minus TDS minus SDT. Put this value of TDS, you will be obtain this one. Now, if you consider at the N and T constant, so you will obtain the expression of pressure. dv only present, and these two are 0. If you consider v and t constant, only mu is present. If you consider n and v is constant, only s is present. So you will obtain expression of pressure, expression of chemical potential, expression of entropy from the Helmholtz free energy. So this is the expression of Helmholtz free energy. So from the partition function you obtain the Helmholtz free energy. After that you will get the expression of pressure, and then chemical potential, and then entropy. Okay, I think clear. In the upcoming also you will be obtain like that. Internal energy U equals to A plus Ts. You know F equals to U minus Ts. So U equal to F plus Ts, and put this value of S minus del F del T. So internal energy can obtain from the Helmholtz free energy also, but internal energy can be obtained from the partition function directly also. So as you is, or question which is asked as like, you just answer this question on this way. So the enthalpy H equals to U plus PV, U equals to M minus this one, and PV, P already obtained here, this one, and V equals to like that. So this is the expression of enthalpy. What is the expression of Gibbs free energy? That is G equals to mu n, and put this value of mu, expression of mu, that is the chemical potential, which is del F del N at constant V and T. So this this gives you this like of expression of the Gibbs free energy. Now comes to the point of the specific heat at constant volume at the fixed number of particles. So del Q del T at constant number of particle at the constant volume. V is constant, N is constant. So dq equals to du plus pdv. Here the V is constant, so that's it. dv is equals to 0. That means dq equals to du. So you can write down Cv equals to del u del T at constant N and V. Clear? Next point is the specific heat at constant pressure. Here also this specific at constant volume can change into the expression of Helmholtz free energy. This is also true. You can find out the internal energy. From that you can get the specific heat at constant volume. But if you want to find out the specific heat at constant volume from the expression of the Helmholtz free energy, you can obtain like that, because you just put this value of u, actually u here, F minus T del F del T. You just put this here of this expression u, and taking the derivative del F del T, and this is the first derivative of this one like this, and second part derivative is this two are cancel out. You can easily find out the Cv from the expression of the Helmholtz free energy. Okay, so minus T del 2 F del T square like that. Now specific heat at constant pressure Cp gives you the expression dq by dt at constant n, number of particle, and p pressure. You know dq equal to du plus p dv. Since p is constant, dp is 0, you can add on this one. This gives you d of u plus pv, and u plus pv is the enthalpy H. So Cv is obtained del u del T, and Cp is obtained del H del T. Okay, this Q is replaced by H, no problem. So their ratio, that is gamma, is Cp by Cv. So first obtain Cv and Cp, and then ratio you will be get this ratio of the specific heats. Okay. Now we need to find out the fluctuation in canonical ensemble. Fluctuation in canonical ensemble. Okay. Fluctuation means the value changes from its average value. Okay, the separation between the value of any data from its average value. So if you taking square, you will be get the square formula of whole square. And now if you wants to find out the average of this one, the r square average, and this gives you 2e average, already average. So this gives you another er average, and this is already average. Actually, if you find out the average of an average, will be the average value, because if you wants to find out the average of 10 number which are same, suppose if you wants to average the 10 student whose age is 15, so the average value will be also 15. That's like that. Okay, so finally you will obtain this expression, this one. Now you can check that u is the expectation value or the average value of energy. This gives like that. If you find out the derivative with respect to u, you will be get this one, and you can see with respect to beta. Okay, so if you take this beta derivative, you will be get this one in the upper side, that is er minus er gives you, and for lower one this upper portion and the whole square of that one multiplied by this one, and you rearrange them, you will be obtain minus of this one. Okay, so this can be written as minus del u del beta. Okay, so this is del u del beta, this is minus del u del beta. So this sigma, that is the canonical ensemble standard deviation root under this one, so root under del u del beta, and this beta can be changed into the temperature. So finally you'll be get this expression. Okay, and del u del t is also Cv. You can write down this as a Cv. Okay, if you want, you can write down this sigma. This sigma equals to root under kt square Cv, which already which is another expression. Okay, And if you want to find out the relative fluctuation means the fluctuation with respect to average value, sigma by u. So sigma is nothing but this one, kt square cv, del u del t is cv, kt square cv by 3 by 2 nkt in case of ideal gas. Okay, u equal to 3 by 2 nkt, cv equal to del u del t, that is 3 by 2 nk. Okay, put this value, rearranging, you will obtain this one. So you can see that is the relative fluctuation proportional to 1 by root n. That's mean for in case of the large number of particle, when n taken as the large number, the fluctuation will be reduced. So if you consider for few numbers of particles and calculate the fluctuation, this will be more if you consider a large number of particles to calculate this relative fluctuation. I think clear. Go to the next topic, that is the thermodynamic function of an ideal gas. Okay, thermodynamic function means thermodynamic variable of an ideal gas. So if you consider a ideal gas with the n number of particle with indistinguishable, that's mean classical, monoatomic, non-interacting and non-relativistic. Okay, since these are non-interacting, there is no potential energy, only kinetic energy, that's p square by 2m. Okay, so the partition function of a single particle will be in 3 dimension, that's why 1 by h cube, integration of in the 3 dimension like that. Put this value of energy p square by 2m. So this gives you the volume spatial, and this is the momentum. This gives you like that, volume in the momentum space will be like that, 4 pi p square dp. So if you integrating with the help of gamma function, you will be obtain this type of expression. Finally, you will be get this expression. Okay, and this can be rearranged into lambda thermal, where lambda thermal is de Broglie wavelength. Okay, I think you can do this calculation very easy. If there is any doubt, any problem, you must comment in the comment box. Okay, so this expression turns into like that, V thermal Q. This is the partition function of single particle. Here, for the partition function of n particle will be like that, z1 to the power n, and this is indistinguishable. Since these are the indistinguishable, you need to divide it by n factorial. So this gives you 1 by n factorial v by lambda thermal q whole to the power n. Now comes into the point to find out the others expression like internal energy. E equals to minus del L beta of ln Zn. So this is the Zn. If you take this logarithm of this expression, n is coming to the okay, these two are separate out and n is coming to the front side, you will be get this expression, because this one derivative there is no expression of beta, that's why this derivative will be 0. And this value, put this value of lambda thermal and taking the derivative is to beta, you will be get u equal to 3 by 2 nkt. I think you can do this derivative, ln of this one, the 1 by this one, and taking the derivative is to beta like that. So this is the internal energy of this system of ideal gas. Then the Helmholtz free energy equal to F equals to minus KT ln Zn. So put this value of Zn and rearranging, then you will be obtain this expression. Okay, and this is a Stirling theorem, that ln n factor equal to n ln n minus n. Use this here. From the expression of Helmholtz free energy, you can obtain the others variable. So Helmholtz free energy expression like put it like that, taking n as a common. So the entropy equals to minus del F del T. So if you derivative with respect to temperature, this will give you minus nk and this minus plus, so nk into total things. Now derivative of this one, so nkt, and this is the 1 by that one, and derivative with respect to t, so this gives like that, and finally will be obtain this expression, and this is known as secular tetrode equation. This will be again comes into the after Gibbs paradox. So the entropy of the ideal gas will be like that. I think clear. Want to find out the another expression, pressure. Pressure equals to minus del F del V at constant n and V. This expression we obtained just before. So use this F and respect to V. If you derivative, you can get P equals to nkt by V. And the corresponding chemical potential will be del F by del N. You will be obtain this one. Okay, so I think you can do this calculation very easy. If there is any doubt, you must comment in the comment box. Enthalpy, U plus PV, put this value of U and V and P, we will get this one. gives free energy mu dn, put this value of mu and n. Specifically del u del t, put taking the derivative with respect to t of cv and c h. Okay, and the ratio gamma equal to c by ct, standard deviation, fluctuation, like that, all can be calculated of the ideal gas. I think clear. If there are any doubt, you must comment in the comment box. In the content, we can see some previous year question. In 2021 and 2015, they gives you this type of question, and we just before uh, prove this expression already. Just you can see this is the fluctuation. The notation is different. E is the energy and E bar is the average value of energy. So it will be get this one, and you know this E average equal to like that and E average square equal to like that. So this gives you the minus 1 by z del beta, and this is 1 by z square del square z del beta square. Okay, so put this E average square like here, this one, and E square average is this one, and E average square this one. So you'll be obtain this one, and this is nothing but minus del E. So this one, and del E by del beta, del E by del beta is gives you minus kt square cv. So you will obtain kt square cv. Okay, very important. In 2014, they wants to know about that is given this partition function, and you need to find out the internal energy and then specific it from this. So this is the partition function. You just elaborate onto this one, and this is gives you the infinite gp series. Sum is 1 by 1 minus r. So this gives you 1 by 2 sine hyperbolic beta h cross omega by 2, where h cross, you know, h cross is the h by 2 pi. So the internal energy from the partition function, you can get the internal energy, that is minus del beta of ln z. So just taking this derivative with the beta, you will obtain this expression like that. Okay, this calculation you can do, I think. So specific heat Cv equal to del u by del t. Change this t into beta by chain rule, you will be get this expression. And the okay, that's already done. Next question says show that the average energy of a system in contact with the heat bath can be expressed as like that. So this is the expectation value, will be like that, where z is so internal energy is like that. So u equals to can be written as like 1, and you can prove this. Okay, this proof already discussed in previous slide. Next question says starting from the canonical partition function of an ideal gas given by this one. This is the partition function. Establish the equation of state. From the partition function, you will be obtain the Helmholtz free energy expression minus kt ln z. Put this value of z. This whole to the power n in the front side. So in the pressure expression del v del f del v with respect to volume, you get this expression. So pv equal to nkvt. This is the equation of state. Okay. Next question says in 2015, a system of n particle contains one-dimensional linear harmonic oscillator whose Hermitian is given like this. This is the Hermitian. Write down the partition function, then Helmholtz free energy and entropy, then Cp, Cv, and then pressure. So for a single particle, partition function will be like that, 1 by h. So Z1 is like that. This is the partition function of single particle. Separate out P and Q using this gamma function. You will be obtain this. Okay. You do this calculation yourself. If there is any doubt, you must comment. So the partition function will be like that. Z1 all to the power n is like that. So Helmholtz free energy minus kVt ln z. Z is obtained here. Put this value. N is in the front side, you will be obtain this one, and the entropy minus del F del T with respect to temperature, the expression will be like that. So internal energy is minus del beta ln z equals to like that. Corresponding Cv and the pressure will be that's one, and Cp. Okay, I think you can do this example and calculation. If you found any problem to understand this one, you must comment in the comment box. This is all about me, and this is my contact detail. You can connect me with this Telegram channel, and this is my YouTube channel details. Go to this channel, you will get different free related videos of mathematics. Like this session if you learn something from this session. Share this video to your friends, either he or she also get benefit from the video. Subscribe this channel if you mean this channel. Those already subscribed, thanks for subscription. Press the bell icon to get notification of upcoming video. So take care. We'll meet on the next video as soon as possible. Thank you.